Alright, boys and girls, let's go ahead and get on to today's homework. All right. In a previous video, I went through the electron configurations of all the elements in the first two columns of the periodic table, and at the very end there I discussed why it is that we call these elements the S-block elements. We're going to move over to this side of the periodic table now. Right, starting up here with element number 5, which is boron. We're going to go over and look at the next 6 elements. So this entire block here. All right, it's going to be what you can see between my hands there. Okay. So what I'd like you to do is do the electron configuration for boron, carbon, nitrogen, oxygen, fluorine, all the elements in that row. And go underneath, starting with aluminum. Do the electron configuration for all the elements in that row. And then underneath that, starting with gallium, all the elements in that row. And then starting with indium, all the way across to xenon, all the elements in that row. And then underneath that, at number 81, thallium, all the elements in that row. And that may seem like a lot of work, but I'm going to go through the first row with you. Now you're going to see that it turns out to be very simple. So let's start with boron. All right, boron has 5 electrons. All right. 5 electrons, number of electrons we'll stick up here. And its configuration, config, it's going to start with, all right, if we get this out, we know it's going to start with 1s. Or we can get this out, and we know that the diagonal line first passes through the 1s thing. Or if you wrote down the sequence like I did a couple videos ago, you just choose them off there. But anyway, 1s, and s's could hold 2 electrons. And then after 1s comes 2s. It also has 2 electrons, and then 2p. Now, I have 2 here, 2 here. That's 4 electrons. I only need 1 more here, so that's 2p1. Boron has the configuration 1s2, 2s2, 2p1. Now, carbon, element number 6, 1s2, 2s2, 2p2. Right, notice I just add 1 additional electron to the p orbital, comparing it to boron. 2p1, carbon is 2p2 for a total of 6 electrons. And then we go to nitrogen, which is 7 electrons. That'll be 1s2, 2s2, and then 2p. What do you think? What do you think? It's going to be 3, right? 2 and 2 is 4, and 3 makes 7 electrons. All right. And then oxygen, it's element number 8, 1s2, 2s2, 2p, 4. If you said 4, you're correct. After oxygen comes fluorine, element number 9, 1s2, 2s2, 2p, 5. How much further can I continue adding electrons to the 2p orbital? Well, what's the maximum number of electrons in a p orbital? Actually, I should say in a set of p orbitals. P orbitals come 3 to a group. All right. We can then, therefore, hold a total of 6 electrons in a p orbital. And as it turns out, neon, which is at the very end of the periodic table, atomic number 10, is the element that in fact takes up the last place. The 6th electron in this 2p orbital fills it up. So we've run out of space in the 2p, and we've run out of periodic table. Okay, we're going to continue on, going down, starting with aluminum and then going over to argon. All right, aluminum is element number 13, and then silicon is 14, phosphorus is 15, sulfur is 16, chlorine is 17, and argon is 18. Now in this column we'll put the electron configuration. Electron config. Alright. Now we have to find a home for aluminum. We have to find a home for its 13 electrons. And again, we could start with something like this and say the first 2 electrons go in the 1s. That's the same for everything. Right? Or maybe like this diagram a little bit better. The diagonal lines, the first one is the 1s. Okay, it's the same thing. Or if you just write down the sequence, just 1s, 2s, 2p, just write those down. All right, anyway, so aluminum will be 1s2, 2s2, 2p6. Right, that would give me the first 10 electrons. And I have to get up to 13. So what's after 2p? Well, after 2p is a 3s, and I'll fill that up with 2 electrons. S's hold 2, p's hold 6, if you recall. And then what's after 3s? 3s is 3p. All right, and all I need is 1 there. If I add up all these superscripted numbers, 2, 4, and 6 makes 10, 11, 12, 13. It's 13 electrons. Now, if I go down to silicon, I have to write an electron configuration that finds a home for 14 electrons. Well, it's going to start out the same way. 1s2, 2s2, 2p6, 3s2, and then we're going to have to put electrons into the 3p. Well, if aluminum was 3p1, then silicon is going to be 3p, that many. And as we go down this list, I just keep adding 1 more electron. Instead of 14, phosphorus is going to have 15. Where does the 15th electron go? All right, and the same is true for the rest of them. Now, by the time I get down to argon, I have to add how many additional electrons into this 3p? 1, 2, 3, 4, 5, 6. So at the very end, argon is going to be 3p6. Can I fit any more electrons? Nope. P's only hold 6. So I've completely filled up a set of p orbitals in going from aluminum to argon. It should look familiar. Go back in the video and look at the electron configurations we did for boron through neon. Now what I'd like you boys and girls to do is a very similar table as this for the next 3 rows. Gallium through krypton, indium through xenon, and thallium through radon. And I will expect that you're going to hand in or submit through Google Classroom a picture of this kind of table for each of these 3 additional rows. All right. Make sure you put into your notebook also the configurations boron through neon that I just did and erased, and then aluminum through argon. Finish that one up too. As a matter of fact, let me change what I'm going to ask of you. Instead of the gallium and thallium, gallium, indium, thallium, I want the aluminum, gallium, indium, and thallium. So there'll be 4 tablefuls of configurations like these. Submit those by midnight tonight, and we'll move on from there the next day.